So this experiment is going to be for a couple of purposes. The first one is we wanted to learn about data acquisition, and that's an important part of engineering analysis where we have very fast streams of data and we want to sample the data. So the accurate sampling of the data and representation will be an important part of the experiment. And the second part is going to be learning about boiling heat transfer and the regimes of the heat transfer curve that comes out as a result of the boiling phenomenon. So the way that the experiment works is that we have a physical system, and the physical system here is going to be a copper sphere that has a thermocouple in the middle, as you can see in here. And this copper sphere is going to be connected to a digital thermometer, and the connection is at the top here. So once it is connected, there's going to be a voltage produced here if the temperature of the center of the sphere is going to change. And since the sphere is very small, and since it is nearly at homogeneous temperature, then we can use a lump parameter model to say that there's no difference between the surface temperature of the sphere and the inner temperature. So whatever temperature comes out will be representative of the boiling process at the surface. We have here a dewar. Basically, let me just put this down here. We have a dewar that has liquid nitrogen. So you have to be very careful not to put your fingers inside. This is very cold at 77.4 degrees Kelvin. And the sphere is going to be dipped into the liquid nitrogen. So the temperature of the surface of the sphere and also the temperature of the center, which will be very close to the surface, will be changing, decreasing. And it will decrease very fast. And it will give us cooling on the surface will result from the boiling process at the surface. So we'll do that in a minute. So let's keep it right here. You have you have to be able to clean the surface. So you have tissues given to you here to clean the surface. You have also acetone that will be used to condition the surface or clean it. And we have Vaseline to look at the effects of surface conditions on the boiling process and also on the heat transfer through the Vaseline layer. So we'll do that in a little bit. Now the voltage signal that comes through, it goes through a data acquisition system, and that goes to a computer, and the computer has software to analyze this data. So the software is called LabVIEW, and it's very common software for data analysis. And the LabVIEW, to access the LabVIEW, you go to the start, and you go to the National Instruments LabVIEW 8.2, and you click on this. So it will activate the LabVIEW, and you have a menu to choose, and you open the data acquisition system, second one from the top, and that will start a program that has been already designed by Ben, and as you can see here on the screen. So for this program, your focus is going to be on the data acquisition tab and then the processing tab. And the data acquisition tab will allow us to acquire the data once we get the stream that is stored in the system, and it also allows us to save the data in files. So you can choose the file where you save the data, and after you save it, you can reload the data and you can analyze it further. And Ben is going to give you a little bit of information on some of the specifics of the software. So I'm going to show you how a typical experiment is done, and then Ben is going to just explain a little bit more. So here's a typical experiment. We have to dry the surface with the tissue. And we have done conditioning for the surface, and then you have actually positive and negative here. So you will connect it. One is wider, like I think the positive is the wider one. Connect it here. And then once you're ready to go, then you will dip it, and then you start to acquire the data. So there's a tab here called Acquire. You click it, and then you will see that we have two curves on the left here. This is the temperature versus time, and on the right here it gives the heat flux versus T minus Tsat. Your data file is going to contain this information, and you'll be asked to actually analyze the information yourself. As you can see from the left-hand side, this is the most critical part of the information, is the temperature of the copper sphere is decreasing from room temperature very quickly, trying to reach equilibrium with the liquid nitrogen. And in the process, you cannot see the fluctuations, but if you expand the scale, you see a lot of fluctuations. When you take the derivatives to find the heat transfer, the heat flux, then the derivatives will give you all of these fluctuations. You can see now that during the close to the Q max, the temperature will drop very quickly, and at the same time, you see, I have to stop this here. Yeah, so now, yeah, so stop the data, and we can save it at any point in time. I think we have to stop it here. So if you look at this curve, there's a reasonable decline in the temperature, and then around the Q max you get a very rapid decrease in the temperature. This is where the fluctuations make a big difference, and that corresponds to the Q max on the boiling curve. So that would be a typical experiment where you have to save the file, and then you will take the file and process later. So I'm going to just have Ben maybe take you on a short tour for starting from the beginning on the data acquisition system itself, the LabVIEW. So I want to just explain.
Yeah, just kind of a very quick explanation of how this software works. First, the name of the software is DataAc_RA. Some of the features that it works is first, as Professor Ghooniem was talking, there's a data acquisition tab. In this portion of the tab, this is where you would acquire the data and save the data. And once you acquired it, if you wanted to acquire another set of data, you would just clear it and repeat that process again. And also another feature is like this load button. It allows you to retrieve old data. And how that works is you basically start from well, let me start from the save portion of it, since that makes a little bit more sense. So what you do is you just press the save button, and then it'll specify the name of or request the name of the file in this LabVIEW space data. This folder is also located in the desktop, so you shouldn't have any trouble finding it. And just going to specify the name. I'll just call it test. And press return, and it's going to be saved in an LVM format, which is a LabVIEW specific format, but it's basically a text file with the first 10 or so lines explaining the details of the experiment, and the remaining portion, the actual time temperature data, in a tab delimited format. So you shouldn't have any trouble exporting it or importing it into your Excel or your MATLAB program. Okay, so that's been saved, and so I'm going to go ahead and clear it just to show you how the load portion of it works. So clear will clear the data, and it actually will clear all since the data is clear, all the analysis that will be done with that data is also clear. So if you want to come and load the data, you just press this folder icon to specify the file that you want to load. And in this case, I'm going to select the test, which is the file that we just saved. Press OK, and then the name of the file that you wish to load is specified here. And just press the load button, and it'll reacquire the data set without having to repeat the experiment. And it'll also do the same analysis. Okay, that's the data acquisition part of the experiment. And the next part I'll talk about is the processing. Once you collected the time temperature data, you'll be working on finding the Qmax of this on the surface of the copper sphere. And to determine those, what you need to do is, like Professor Ghonim was saying, determine the dt, the capital T, d lowercase t, which is time temperature derivative. And it's a bit of a problem because normally it's you know, I'm gonna zoom into some of this graphs to show you how the problem arises. Is at this lower portion of the time temperature, you see a lot of noise within this zoomed time temperature data. And when you try to take a derivative of that, you end up getting or you basically amplify the signal with the small time steps that you're taking the data. So it results in a very large noise in your derivative, which makes your Qmax measurement meaningless. So we've developed this set of functions up here that will allow you to process the data in a more meaningful manner. Okay, so I'm going to just go ahead and zoom back out here. And some of those things are the running average. Basically, we take a certain number of data set before and after to smooth out some of the noise for that data point, and you specify the number of data points that you want to measure by just changing this n value. It currently is 8, so I could go ahead and change it to 1, or if I was to change it to 1, you could see that since we're not averaging as many data, or we're not performing the running average since we are performing a running average over a smaller set of data, you see that the derivative, or the heat flux, or the derivative from it, there's a increase in the noise that we see here. Okay, and the next feature that we have is resampling. It's basically allows us to through software resample at a different rate. As you can see, originally it was the sampling rate was at 100 hertz, 100 samples per second. What we can do is change the resampling, which is this K factor. So K is specify the number of data point that we're going to be looking at. So 1, we'll be looking at every data point, and then if we were to change that K to 2, we'll be only looking at every other data point, which change the effective frequency to 50, and so on and so on. So you could modify that K value to get the effective frequency that you like. Okay, and the next parameter that we're going to be considering is the differentiation. There are 2 different differentiations that's built into the software. First is the center difference, which everyone should be very familiar with. This just, you know, looking at the point before, looking at the point after, and then dividing it by some difference in time. And if you're using the center difference, the side points parameters does not affect your analysis. But since at least in the let me get back to our noisy signal here. So if we were to use this running average of 1 and the resampling at 1, then we still get a fairly noisy peak here. So if we were to change it from a center difference to a Savitsky-Goulet, which is just a fairly fancy smoothing routine, it allows us to have a much cleaner signal. As you can see, most of the noise has been essentially eliminated from our heat flux versus T minus T sat graph. Okay, and then you could also change the side points. Side points is basically how big of a band you want to consider in your Savitsky-Goulet routine. So the higher the number, the more the smoothing you're gonna be applying. Okay, and you could change that number just by pressing the up or down button. And the last item that I want to talk about is this software is also built to automatically determine what the Qmax and the Qmin should be, and it's basically what this peak is, where this peak is. And just due to the different operating conditions, it's the T minus T sat over which the Qmax occurs changes. Currently, it is at 10, 20, 30, 40. It's happening around where T minus 40. And in this region, we specify in these two tabs, we specify the T minus T sat, the lower and the upper limit that we want to determine, we want to use to determine Qmax. So right now it's 40, which might be just a little bit beyond what the Qmax should be. So I'm going to increase that to 50 just to make sure we capture the peak. And as you can see, the Qmax went slightly higher just because it appears that the Qmax occurs just a little bit above the 40 degrees that we had previously specified. And the last thing that I want to talk about is once we taken a look at the data that we collected and processed it in the various manners, we can go ahead and save that file. So this file, it's going to be slightly different from the raw data that we previously saved. Previously, the raw data only has the time on the first column and the temperature on the second column. None of the processing features that I've just talked about. But this second save button, Q versus T, that's going to include, in addition to the raw data, time and temperature, it's also going to determine the D capital T, D lowercase t, the derivative of temperature with respect to time. And that will be using these parameters that you have specified. So what you can do is specify the analysis conditions and then press this save button and then name your file. Again, I'll name this test2 just as an example. And then press OK, and it'll save that file for you to do additional analysis, which Professor Ghonim had talked about. And that's it.